All right, so welcome to the seminar in the analysis and methods of PDE. Our speaker today is Kavita Ramanan. She's the Roland George Dwight Richardson University professor and associate chair of the Division of Applied Mathematics at Brown University. Her research interests are in probability theory, stochastic processes, and their applications. Her research has received many recognitions, including Senior Scholarship, one of our Bush Faculty Fellowship, Goodham Fellowship, Simons Fellowship, and Erland Prize from the Informs Applied Probability Society. She's an elected member of the American Academy of Arts and Sciences. She's a fellow of multiple societies, including IMS, Informs, and SIAM. She's now the IMS president-elect. She's also interested in math communication, initiated the social equity and applied math seminar series, runs a math outreach group called the Math Co-op, and organized the Mathematics and Frontiers lecture series. So without further delay, so we welcome Kavita to speak to us about long-time limit of nonlinearly coupled measure-valued equations about that model many server queues with reneging. Oh, the title is H-theorems for queues with reneging.
Okay, thank you so much for the kind introduction, and thank you so much for the SIMA organizers for inviting me to give this talk. And let me first acknowledge my collaborators, Rami Atar, Weining, Kang, and Haya, Kaspi, all three of them who are my co-authors on the paper for which this talk was selected, and which appeared in SIMA in 2023. So let me start by, I will start by talking with the model, give you a particle description of the dynamics, and then the nonlinear PDE that describes the scaling limit, and then talk about these H-theorems, discussions of the proof, and touch upon many open questions. And I encourage the authors to stop, the viewers to at any time, just stop and interrupt me as you go if you have any questions. You don't have to wait till the end. Okay, so let me talk about the model and the motivating questions. So we just take a very, very simple model, which is that you just have a common arrival process that's coming into a network of servers, which are just simple parallel servers. And the packets queue up if all the servers are busy, and they're put into this queue. And these servers are all assumed to be n identical servers. And this total arrival process, En of t, is some stochastic process that keeps track of the total number of arrivals that came from 0 to t. And you want to think of lambda n as sort of the long-term arrival rate, so the sort of the expectation of En t over t. And then you have each of these are sort of identical servers, and they're all serving at some rate, and without loss of generality, we can set this rate to be 1. Okay, and so how do these those waiting in line get allotted to the different queues? Well, that's just in first come, first serve. So the first come who comes in, you just get queued up in order of your arrival, and the person at the head of the line gets served as and when the servers get idle. Okay, so this is a very, very classical and very simple model at one level. And so we will always denote by Qn the total number of jobs in queues, or Xn here actually will be total the number of jobs in system, which will include those in service. Okay, so where do such queues arise? They really arise ubiquitously. For example, when you call on the phone and you have some question to ask some call center, then you are actually queued up, and then you are routed to these different servers. It arises in healthcare when you're looking for a bed. It arises in data centers where now what's coming in are not customers, but they are actually packets, and so on. So there are many, many applications. They also arrive in biology, where now you don't think of you think of your queues as not in terms of people, but really they're sort of enzymatic processing networks. So these processing networks are there all over. So here, when the enzymes are really the ones that are processing, so they're sort of the servers, and you have reactions that come in, those are the arrivals, and the departures are in terms of products. Okay, so there are many biological and problems that can also be framed in terms of this kind of queuing networks. Okay, so what is a quantity of interest in these kinds of networks? You want to understand what is the probability that the amount of time that the person is waiting, or the packet or the reactants are waiting in line before they're actually served, is greater than some level, W, or that even what is the probability that there's a positive wait, that they don't get immediately served, right? So when W is equal to 0, you may ask. And you want to ask this in equilibrium, okay? Okay, so, and so you want to understand sort of the stationary or equilibrium possibilities, but these, for many applications, you don't have just this simple network, but you also have to require the incorporation of reneging. So let me tell you what that is. Well, if you have n independent, again, identical servers, you have this common arrival process En, and now each of these jobs, which could be, like we said, reactants or customers or packets, they also come with a sort of patience time. So there's an amount of time that they will wait in queue. And if that time expires before they get served, they will leave. So of course, we can think of that in terms of people as just some patience time. But in terms of other applications, actually in enzymatic processing networks, this becomes relevant because this is sort of something that's called dilution. So in effect, you can model that as reneging. So the reactants sort of start leaving where they are waiting for, and that's a sort of a patience time. So you assume that each packet or each job or each reactant comes with this patient time and a service time, and all of these are independent, and they're independent of the total number of arrivals. Okay, and we will always assume, now you also have to assume how much time do they spend actually? What is this patient's time? How is it distributed? So you assume that the patient's times are coming from some distribution, which we call GR, R for reneging, and also the service times are coming from some other distribution, which is some GS, okay? Okay. And now, like I said, you don't have only the arrivals, you have the queues that are waiting over here, but you also have reneging from the queues before you get into your queuing system, and then all your server system, and then you will have departures. Okay, so departures, so what you do, typically a person will come, they will spend some time here, and if they get to the head of the line before their patience expires, then they will go into the server, then they will spend a time VJ over there and then exit. Okay, I hope the model is clear. But however, if they come here and they're waiting here too long, and they haven't got to the head of the line before their patience time has expired then they will just leave the system without getting any service. Okay, so these are sort of the quantities that we will assume. And of course, even in the reneging time, we're always assuming that you have a first come, first serve, non-idling scheduling discipline. Okay, so of course, even though this is quite simple, if everything is exponential, that is that all the service times are exponential or all the reneging times are exponential with some other parameter, then you can actually analyze these quite nicely because the system state is nice and Markovian, and you can take some limits and understand how these systems behave quite nicely. And this has been done by a variety of people, including Garnett, Mandelbaum, Ryman, etc., and Halfin and Witt. But however, the exact analysis for a finite n, when you have general service distributions, which is a more realistic model in all these applications that I mentioned, statisticians have looked at sort of what are the service time distributions in call centers, others have modeled things in hospitals, so you know that you can't just assume exponential service times or exponential distributions. So in that case, analyzing this for a fixed n is really not very feasible. However, one knows that as long as for any lambda, you can assume that quite general results in stochastic processes tells you that you know that the system will have, as t goes to infinity, some steady state distribution. Okay, because the reneging means that it doesn't matter how large the arrivals are, you will still have some steady state distribution. And so the idea in the asymptotic analysis, we want to try to understand the steady state distribution, if you remember the quantities of interest. But the idea in this asymptotic analysis is, well, of course, you know that the system is growing sort of proportional to n because the arrival rates are being scaled with n. And so you can see that if you sort of look at the renormalized Q length or number in system, then you expect a process level convergence. You want to try to prove that this y hat n divided by n goes to some more tractable limiting dynamics than the original stochastic process. And once you get these limiting dynamics, you want to sort of analyze that. And then you say, okay, maybe this is more tractable than the original. And if so, maybe I can understand this process's unique invariant distribution. And if I can, then maybe I can try to see, oh, maybe that this unique invariant distribution, if I can make this diagram commute, might serve as a good approximation for large n for my steady state distribution, which is the quantity of interest. Okay, so that's the general idea in the scaling limits for processing networks. So let me start by going back to our dynamics and focusing on the server side of things and looking at what is a nice particle representation of the dynamics. Okay. So over here, what you have is, again, remember that you have things coming into the queue with total cumulative arrival. You may stay in the queue, and these are all the servers. In this particular case, they're all busy. Now, when you have non-exponential, if you want to try to get some nice dynamics, like in terms of some PDE in the limit and the scaling limit, you want a nice representation in the prelimit in terms of some Markov process. Now, we know that when you have an exponential distribution, then what that really means, it's equivalent to the following, then how long I have been served does not matter to determine whether or not I will finish service at this particular time. Okay, that's the memoryless property of the exponential distribution, and that's the only continuous distribution that has that property. However, let's say that you have a distribution that's sort of uniform, let's say between some A and B, then you of course know that if you've been already served for you have already been waiting for, sort of B minus A minus epsilon, then you know that you're very likely to be served, right, in the next epsilon units, because you know that you're uniformly distributed in AB. So there, the amount of time that you have spent in service will affect what is the likelihood that you will, leave the system. And so this can be captured nicely by what is called the hazard rate function of the distribution, which is simply the derivative of the distribution. So this is the density divided by 1 minus the probability that you have so this is really the probability that you have not yet departed by time x, or not yet been served. Okay, so this hazard rate function is really capturing this. So this is just saying, what is the probability that I will leave between x and x plus dx, given that I have not left up to x? Okay, so that's sort of what the hazard rate function is capturing. So what we need to do to keep a Markovian representation of the state, like I said, because we don't have exponential distributions, is you want to keep track of the ages. By age, I mean the amount of time spent in service of all the packets jobs that have been in service at time t. Okay, so over here you have 1, 2, 3, 4, 5 particles that have been, or jobs that have been in service, but that's not enough to tell me what the departure rate will be at any time. However, this right-hand side, this graphical representation, will allow me to do that, because it tells me how much time I had this particular, maybe this particle has spent this much time, this particle has spent this much time, etc. So the x-axis tells me how much time I have been in the system at time t. Okay? And we can look at these as sort of Dirac delta masses on the interval 0 to infinity, giving my ages. And if I sum that up, then I get my age process. Okay, and now this age measure, it's a measure valued process, right? Because it has a Dirac delta mass at each of the ages of all the customers in service. Then you know that this is enough to tell me how to evolve in the future. Okay, so of course you could have also just said, why don't I just keep track of, this n-dimensional process? But we wanted to do it in terms of a measure because we want a common state space for all n, because we're going to take n to infinity. So if you have a state, Markovian representation of the process, which is n-dimensional, it's hard to think of a limit because you're going to send n to infinity. So the dimension of the state space is changing. So instead, it's clear that you must take an infinite dimensional state space, which in this case is conveniently represented by a measure. Okay, so if you look at this new Tn, you know that the maximum number of such particles can be n because there are only n servers, right? And each of these particles only represent the age of some particle in the server. It could be less than n if there are less than, one of the servers is idle. Okay? Okay, I hope that this measure valued representation is clear. So as I said, we know now from the age that the conditional mean departure rate, and you can make that explicit, will really depend on this hazard rate function evaluated at the age of that particle. So each particle you can think of is leaving with a rate h of its age. Okay, so that's the rate at which you will departure. That's a way of capturing a general service distribution. So even if you are not familiar with all the stochastics, you can just think of this as a process where things are coming in at rate lambda, and then you have ages for each of the states, and they leave at a rate of h evaluated at the age. Okay. And so now, of course, we know that we all inexorably age at a unit rate with respect to time. So all the particles move at unit rate to the right. So just to understand what is the dynamics of this process. So all the particles move at unit rate to the right, which is just saying that they have been in the system, as I showed that they move here. And then the departure process is, like I said, all the H's that the total rate at which they leave over here. And then there's also an arrival process, which is entry into service, okay, which is this cumulative arrival into service, which is this Kn. Okay, so I hope we have this measure valued process on the 0 infinity. And if when nothing else is arriving or departing, it's just simply moving to the right. But when something departs, of course, you just have this at rate h, depending on the shape of the curve, you will have this departure. And everything that's coming in is always coming in at 0, because when it comes in, it has spent 0 time in service. Okay? So there's this cumulative entry here at 0, and then you have everything moving and then leaving at h. Okay. So that's really the full dynamics of this process. And we, of course, want to now, this is in pictures, so we want to try to write it in terms of equations. But let me just tell you that one can prove explicitly just that the expected value of the total departure is nothing but the integral of this hazard rate with respect to this measure taken at time s and integrated over time t. Okay, is that clear? Because I'm going to use this bracket always to denote integrals in 0 infinity, which I think is quite common in PDEs as well. Okay, so it's sort of this duality nu s h. Okay, so one can prove this. Now, of course, we actually have a more complicated system, though I'm going to focus on just the service, but we have actually a corresponding measure that we will call eta, which is also taking care of what's happening at the queue, right? So somebody comes into the queue, they wait for some time. The rate at which they will leave the queue is again a hazard rate, but now it's the hazard rate of the reneging distribution. So they are leaving at some rate. And they go in here depending on when these customers become free. And so this is really the whole process. And the En is given, okay? So the dynamics of the queue is very similar to the dynamics of the service, except with a different hazard rate. But the only two differences are the time when something goes from here to here depends on what's happening in this queue. And in the queue, you just have some external exogenous arrivals. But in the service, you will have arrivals that depend again on whether or not you have less than n servers occupied or all n servers are occupied. So whether or not you have idle servers and you have something in the queue, then it goes in. Okay, so that's in part of the model, but now let's then go directly to the scaling limit and the PDE. But I hope that knowing what the model is will give you insight into where the terms of the PDE are coming from. Okay, so if you scale all these quantities in this particular way, right, you divide by n, because as I said, they're all order n quantities. Then we showed in joint work with Haya, Kaspi and Weining, Kang, that the whole process, the whole state converges to some limit, and all the auxiliary processes converge to a limit, and the measure valued process also converges to a limit, where nu satisfies a certain measure valued PDE that I will explain in a bit, and where this total departure process, as we saw earlier, because the expected value of the departure process, right, the sort of the deterministic part of that, the expected value of that was, remember, the nothing but the integral over time of the integral of the hazard rate with respect to the measure, and that remains the same in the limit. Okay, so you have this nice thing that the departure is given just as a function of nu t, which is exactly why we wanted this to be Markov, that because then you can gauge what the departure rate is by just looking at this measure. Okay, and so there were previous results or special cases of this hydrodynamic limit theorem, which are mentioned here, but I will not go into those details. Okay, so now let me explain what this measure valued PDE looks like. Okay, it's a simple transport equation at one level. So if you take any functions on time and space, so that's just 0 infinity squared, then of course, what is the contribution? What is my measure going to look at, like if I integrate it with respect to test functions at any time t? Well, I will have a contribution due to the initial mass, right? So which tells me the initial distribution of all the jobs in service and what their ages were at time 0. And then you have this contribution, and this, if you know, this is just simply a transport equation. This is just the one that's saying that we are all going to move to the right if nothing else happens, right? And that's why it is, because we say that you move to the right at rate 1, so it's something in the direction, 1 direction, which is phi x plus phi t. And then this part, as we saw, is related to the departure process. So it's the hazard rate function, and it's, you know, what you're going to remove out. And the final part is what's coming in, which was due to this, this arrival process K. Okay, and remember here, very importantly, you have only it arriving at the point 0, right? The entries are all at the point 0 because your age when you come into service is 0. Okay, so if you don't want the measure valued, if you just, you know, sort of assume that your nu is nice and smooth and has a density, then you can write it even more simply in terms of a PDE. Okay, so I will formally switch between this measure valued and the PDE so that it's sort of more familiar, it's more classical, even if you can't always justify the smoothness of the F for the generality that we want in terms of the service distributions. But I think it will be very useful to look at this in order to figure out where this falls in within the framework of PDEs. Okay, so really, if you look at this, this is a simple transport equation with a linear right-hand side in terms of H. But what is difficult over here is that then you have the sort of boundary condition, which is really this small kt, which is the derivative of your total cumulative arrivals into service. And of course, this is just an initial condition. And the whole point is that this arrival into service over here, what is that? Well, if there is nobody in the queue, okay, so in particular, if the total number of servers, there is somebody who's idle. If somebody is idle, then clearly there's nobody waiting, because I said if anybody is waiting, they will immediately rush to a server that is idle. Okay, so this condition here, that the integral of the measure, the total mass of the measure is less than 1, means in the n server system that there is at least one server that is idle. Okay, that is not busy, because remember we had a particle for each server, and if there's no particle, then the mass is less than n. So in any case, this BT tells you whether or not there is some idle capacity in the server system, and if BT is equal to 1, then all servers are busy. Okay, that's the way to think about it. So if there is capacity, then there is really no queue, and therefore whatever's coming into service is exactly what was arrivals, and that was lambda. However, if everybody is busy, then the rate at which things come in is exactly the rate at which things are departing, because servers get idle at the rate at which things depart, because that's when they get idle. So that is exactly, this is the departure rate. Okay, so that's hopefully, but now we can just look at it as a PDE, okay, and then see, okay, what makes this difficult to analyze? Well, it is really the boundary condition. So you have a linear transport PDE at one level over here. This equation is reasonably nice, though I will tell you some subtleties about that in the next slide. But over here in this boundary condition, you first have a discontinuity. It's not continuous, either in time or in space or anything. It's discontinuous, because you could suddenly have the BT being less than 1, suddenly it'll jump from lambda to this quantity, which is not related to lambda. It could be greater than lambda, less than lambda, it could be anything. So that's one thing, there's discontinuous. The second thing is this KT depends on the entire, it's non-local, right? So it's non-linear, it's non-local, because it depends on the entire distribution and not just on the value of the distribution at 0 or some point. Okay, so it doesn't depend on f at a point, but the integral. Okay, and the discontinuity. So that's what takes this outside the framework of, but nevertheless, we can try to, and if you look at sort of the same equation for the Q, it will have a similar structure, except that now this is simpler and the KT will always just be lambda. What's coming in is always lambda. Okay, so that equation is quite easy to analyze. Okay, but now we look at this, and now we want to find out what is the invariant state for this equation. Okay, so if we set this equal to 0, right, then we just want to solve this equation. We want to look at a solution that doesn't depend on time. Then you can rewrite this equation in terms of this f prime x, and you can solve it. And you'll see that when lambda is greater than or equal to 1, you can see that this f star x suggests that your rate will be 1 minus g of s of x. So if you sort of just ignore this part of the equation, which you cannot do in the end, but suppose you ignore it, then you can see that one invariant state is given by f star x is equal to 1 minus gsx. Okay, so we have a candidate invariant state for this equation. Okay. Now, so I will denote by mu star dx, just to be this. If it's a similar calculation when lambda is less than 1, you can see it's lambda times this complementary CDF. Okay. Okay, so now let's look at the challenges in the analysis. As I said, though the invariant state is unique, there may be invariant distributions that are not concentrated on the invariant state. What I mean by that is if you start at a random initial condition and you see how this measure flow evolves, there's nothing to say that that doesn't give rise to some other, there might be other random initial distributions. If you start at a deterministic point, we know there's a unique invariant state. But if you start at a random initial distribution, there's nothing, at least this proof doesn't tell us that you don't have some other random possible invariant distribution. Okay. So the boundary conditions, as I mentioned, are nonlinear, non-local, and discontinuous. And we have this, that's the challenge in the analysis. Okay, so you can think of this measure-valued PDE, which I've written in a classical form here, as sort of our key problem that we want to study. Any questions so far? I hope the model and at least the PDE is clear. Okay. Okay, so let me explain the main result and then tell you. Yes, please.
Hello. Yeah, there is a question from audience.
Yes, please.
So the question is non-isolated or isolated essential singular for the particle server. I don't know what that means exactly, but okay, so can you see the?
I do not see anything in the chat, so there is. Oh wait, let me see if I can see. Oh, maybe it's in the question and answers.
Yeah, question and answers. There's one from
I don't have permission to see. Oh wait, I don't see the.
see
Maybe
there's
read it out because I cannot see the
okay,
question.
so there's a question about the singularity for the essential. I mean, it's not clear what the okay. So now a second question is a PD a kind of a Kolmogorov equation?
So no, it is a transport equation of this measure valued PDE.
Right.
So it's coming as a limit. It's a scaling limit of the measure valued equation at the pre-limit, right?
Okay.
So remember, I had this particle representation and I had the dynamics that can be expressed in terms of a stochastic evolution equation for the measure. And if you take the limit, then you get this stochastic, you get sort of this measure valued PDE, but for simplicity, I've written it in the form of a regular PDE, assuming that your measure has nice densities.
Mm-hmm. Yeah, that's from okay, I think those are all the questions from the
yeah.
now
I mean, so our full analysis does not require this, but I think it's useful for a PDE audience to look at what it would look like when you have a density, and it also motivated us to figure out how you might analyze it and how it actually goes outside the framework that is currently known for PDEs.
Mm-hmm.
Okay, so let me say the main result. So of course, remember that I said, of course, that we have some assumptions that we have to make, of course. So we have this reneging distribution. So you remember that what's coming in, suppose the system is busy all the time. So suppose your lambda mean arrival rate is less than, so remember that we are assuming that the arrival rate of the n system is lambda times n, and there are n servers each working at rate 1. So if lambda is less than 1, you don't need any reneging, you expect the system to be stable. But if lambda is greater than 1, you would imagine that all the servers will be busy all the time. And so you have departures at the rate n, right? And you'll have arrivals at the rate lambda n. So if you divide by n, the difference is lambda minus 1, right? And so that's where this lambda minus 1 comes. It says it's the excess capacity. And if you solve this, and then you look at lambda times gr of x is the rate at which you are having reneging. And so you can see that if you look at this equation and you have a unique solution, this will tell you how many people on average are there. Sort of as a heuristic, you expect how many in equilibrium, what would be the average number of people in the queue if the servers were busy all the time. Okay. So in any case, we assume that there's a unique such queue, and this is it's a mild condition. If GR has a sort of non-zero density, then that always holds. Okay, so we assume that this equation has a unique solution, which, like I said, is true for a large class of reneging distributions. And when lambda is less than 1, I will just simply set x star lambda to be equal to lambda. Okay. And now you recall that the GS is the cumulative distribution function of the service times. And we also assume some conditions on the service distribution, which is that it's bounded below and above. Either this is not both. So either I have B1, which is that the hazard rates are bounded strictly below and above, so away from infinity and away from 0, or we assume that the hazard rates are monotone decreasing. Okay, so H is a monotone decreasing function. Okay, and there are several examples of distributions that are non-exponential that satisfy these conditions. Okay, and phase type distributions are a large class of distributions that are actually dense in the class of all service distributions. So all probability measures. Okay, so I won't go into the detail of what I have, but I'm just saying that these are satisfied by a large class of service distributions. Okay, so let's go back and talk about the long time convergence. So remember, this was the dynamic, hydrodynamic PDE and the scaling limit that we had. And the state of the system is represented by the total number in system and then the new t, which is the measure valued age in the service, and eta t, which will be what is there in the queue, which I'm not going to spend too much time on. It's much simpler than nu t, so we can concentrate on nu t. Okay, and I said, like, we can talk about the hydrodynamic PDE with random initial conditions. That just means if I start with a random initial condition, I say it's a solution. If omega by omega, it's a solution of the deterministic equation. And an invariant distribution is said to be, as opposed to an invariant state, is any random initial condition which remains the same under the flow. Okay, so it's invariant to the flow, but as a distribution, not as a deterministic state. Okay, I hope this distinction between invariant states and invariant distributions is clear. Okay. Okay. So then the main result is that if you, for every lambda, if you have this assumption A holds, then you have a unique invariant state for the fluid equation. That means if you start with a determinist initial condition, this is the only thing that you can land up with. And the main result is that you actually converge to this dz lambda star is the unique invariant distribution, and we converge to this unique state irrespective of how you start in the hydrodynamic PDE. Okay, so as a corollary, then we get this interchange of limits that we want, and we're able to say that the z lambda star is actually approximating this n level distribution. Okay. So now let me go back and let me tell you what is the idea of the proof, which might be the most interesting part of this. So as I mentioned, the title was like an H-theorem for PDEs. So let's start with what is an H-theorem. Of course, it goes back to Boltzmann and kinetic equations, but it's maybe more well-known in the case of the Fokker-Planck equation. So if you take smooth V and you take this Fokker-Planck equation, you know that the invariant state for this, or invariant density, whatever you want to call it, is F star is e to the minus V. And the H-theorem idea is to show convergence to the invariant state using relative entropy as a Lyapunov function. So you want to show that along the paths of the Fokker-Planck, the relative entropy decreases and with respect to the invariant state. Okay, so for any function g, you can define this generalized relative entropy functional in the following way. So it's just, you're looking at the ratio of g to the minus v and then integrating with respect to g. Then you have the Fokker-Planck equation, you have this relative entropy functional, then one can easily show, you want to try to understand Ft is the solution to the Fokker-Planck equation. Then if you look at the derivative of this relative entropy functional with respect to the invariant measure, then simple calculus will show it has this form. And if you look at this form, then you know that this integral over here is nothing but what is called the Fisher information of Ft with respect to F star. That's just by definition. This is the definition of the Fisher information. Now, in order to get control of d by dt, we want to show it's less than or equal to 0, or you want to get rates. You would like to relate this Fisher information back in terms of R, right? So that you can get some bound an RT and solve that. And indeed, if you can show that the Fisher information is lower bounded by some strict constant that is greater than 0 of the same relative entropy, then of course you have this nice equation and you will get exponential convergence. Now this step is usually, you get this from some log Sobolev inequality. Okay, so you know that the Fisher information is less than or equal to some R. You often use log Sobolev inequalities to get this. Okay, so similar relative entropy methods have been used for other equations of transport type, which is more like ours. In our case, this V, it has the H in it. And for kinetic equations, it goes back all the way to McKean in 1966, of course, in Boltzmann in the non-rigorous setting. And then there have been many, many results in the spatially inhomogeneous case. And this is an incomplete list. And then age-structured models, which is in biology by Pertam and Mischler and Fournier and several Rizek and other authors. So these are also in biology. Also, it's very natural to keep track of this age because you're thinking of sort of populations and their reproductivity and their death depending on their age. So their age-structured models have been studied, and their long-term limits using a variety of methods and also some relative entropy-based methods. Now, the equations that have been used to study these, the spectral case, really need complete linearity, which we don't have. As I told you, we have nonlinearity due to the boundary conditions. And they also use the relative entropy base, but then they don't have these discontinuities in the boundary conditions. So we can't quite use any of the results that exist. And there have been some measure-valued queuing models other than the ones that we've studied, which have also looked at trying to use some generalized relative entropy for Lyapunov functions. Okay, so let's go back to our measure-valued equation and look at, remember, this was the dynamics with some, or the PDE form, which might be easier to see. And remember that you have this sort of dichotomy, that is, if there is sort of capacity in the server system, which is what you should think of this as saying, then your arrival rate is lambda. Otherwise, your arrival rate is your departure rate when you are at capacity. So, like I said, the invariant measure is sort of what you would expect if you are at capacity always. But even when lambda is large, you cannot expect that you will be at capacity always, because you could have moments when you dip below. And so that's really makes this, to control the oscillations of this BT makes this problem really difficult in terms of understanding the long-term limits. So let me give you some idea of the steps of our proof. So of course you have this measure-valued equation, and I told you that you can think of it as a transport PDE. So I can write this in the weak sense. In a weak sense, this is really this transport PDE with a right-hand side with h times nu plus psi. Now you think of nu as a distribution, so you want to think of this as a distribution-valued PDE. But the problem here is that usually h nu makes sense for a distribution only if h is nice and smooth, right? We know that you can't multiply a distribution by a function unless the function is smooth. And h is also not integrable in our case. A hazard rate function is never integrable, it's only locally integrable. But despite that, we did some analysis in joint work with Haya Kaspi by showing that even though h is not smooth, because we have some regularity along some directions, we can still make sense of this transport PDE and solve it partially in terms of this k process. So you can write this psi t by just sort of solving this and writing it in terms of two terms. One that is just related to the initial condition. So this is just saying that, okay, I have some initial mass, which is being decayed because, you know, things are departing from the initial mass. And so that's one contribution. And this is saying this is all the contribution that I have due to everything that arrived after time zero. Okay, so you have two contributions. And so this thing depends only on nu zero, and this depends on your k process, which of course depends on the q, but I'm not looking at that interaction for the moment. Okay, and now the first term on the right-hand side, you can easily show converges to zero if you have reasonable, nu zero, just from the fact that as t goes to infinity, your complementary distribution g bar x plus t goes to zero. And that's just simply saying that at some point I have to depart, right? Because if I came at time, I was already there at time zero, then I will be leaving the system. As t gets larger, it's more and more likely that I'll leave the system, and I will have to depart. So really the first term is not the problem, and the second term is all that we have to look at. So we can write as psi nu t as kind of psi of this term and then a contribution due to ks. And so let me just call nu tilde t the main contribution due to everything that's coming in. Okay. So now the thing is to, again, try to use relative entropy. So what we do is we use this relative entropy, and the calculations here are more involved than, but you can show that the relative entropy, and this is a generalized relative entropy because remember our nu tilde t is not a probability measure. It is just some generalized measure. It could be a sub-probability measure. So you write this sort of generalized relative entropy functional, and you do some calculations like you did in the Fokker-Planck case where you got some Fisher information on the right. But here we get this quantity. And now the problem is you have this ks log ks, and you want to sort of relate it back to something that you really know, and you want to get the rates as RT goes. But this is, again, discontinuous. So I'm just going to give you a flavor of the proof, obviously not all the details. So I just want to say that what we have is now a key inequality that plays the role of a log Sobolev inequality normally. And so what we have is some sort of inequality, which you don't have to sort of digest fully. So we have the sort of log of this HFT dx plus C1, where C1 was the lower bound on H, times this sort of relative entropy. So because really what you have is you want to bound this again below in terms of relative entropies. And so what we're able to do is, okay, we have this term here plus another term which looks like a relative entropy. Okay, and now I want to tell you what is the key problem that comes up in the analysis of this process. And the main process, and remember I told you this BT is to think of when all the servers are busy and when they go down. Now, even when your arrival rate is really large, you would think, okay, in an overloaded system, the servers must be busy all the time. But because you have reneging, that need not be true, because suddenly you might have a lot of reneging in your queue, and so you have sort of an empty queue, and there's nothing coming into the servers, and you might go down, right? And then again, you have a large arrival rate lambda that again fills up the queue quickly, and then you go up again. So you know that you will hit, you expect your busy time when lambda is greater than 1 to be hitting 1 infinitely often. That is, you'll be at capacity infinitely often. But the key problem is, can you keep oscillating? Okay. And so controlling these oscillations is a key point. And what we have to do is sort of control what happens between these different excursions. We can do some sort of estimates. Then we have to show some integrability of this gamma, and then conclude that this RT will in the end be less than or equal to 0. Okay, so of course I don't want to give you all the details, but some idea of what are the sort of new aspects that come up here that do not come in the study of age-structured models in other contexts. And then you have to show that there exists a large time such that you always remain busy after that time. So you control all the oscillations, and then you want to say that there are no more oscillations. And for that, you use a certain argument by contradiction, using all the estimates that we got earlier. Okay, so that's just to give you a rough idea. That was under assumption B1, but under assumption B2, you use quite different arguments using nonlinear renewal equations. Remember, the assumption B2 was the assumption that the hazard rate is non-decreasing, and that covers all a large class of distributions. So, okay. Okay, so I think in the interest of time, I will just summarize now, and I would say that so what we have really demonstrated is that this use of these H-theorems and a generalized form of relative entropy is useful for studying the long-time behavior of a class of non-standard measure-valued transport PDEs that arise in the context of stochastic networks. And these non-standard PDEs are characterized by sort of, in the interior, they're reasonably well behaved if you take care of this H being not smooth, but in the boundary, they have very non-local and non-standard boundary conditions that fall outside the domain of many of the classical age-structured equations. But however, even with all of this, we still had to put some assumption on the service distributions. And so one of the questions is, can we use more refined PDE or other techniques to show these long-term limits without, these assumptions of, the H being strictly away from 0 or bounded. Though I should say that even in the age-structured literature, where they have a similar H, which is really the death rate of your particle, then they also assume that this H is strictly bounded away from 0 into infinity, even without the boundary condition issue. So even with nicer boundary conditions, the current results actually assume this boundedness. So it would be really nice to know if that can be removed, and also the technique generalized. But more generally, there are also other measure-valued processes. For example, if you look at more complex models, which are randomized load balancing models that arise in stochastic networks, then you actually have a coupled countable system of these measure valued processes, which have slightly more involved transport PDE dynamics. And it's been a long standing open problem actually in the literature there to understand the long-term limit. So we've in work with Pooja Agarwal, we understood the invariant distributions of these models very well, but it's been a long-standing open problem posed by Bramson and many others to actually understand the long-time behavior and to show that it actually converges to the invariant distribution. So that's, can we sort of extend and use these relative entropy type estimates or more complicated issues to understand these dynamics? And of course, are there other models that arise in maybe models in applications that some of you in the audience are concerned with that actually have this flavor of age-structured and age-valued, for which maybe techniques that have been developed in queuing could be useful. So I believe that this whole area of measure-valued PDEs and their long-time limits have a lot of synergies in across very different applications. And I'd like to thank again Seema for inviting me to present my work with my co-authors. Thank you.
Thank you, Kavita. That's a very interesting talk. Any questions from the audience? I think we go with the Q&A. So how does this work with the panelists?
I'm not able to see the Q&A for some reason.
There's nobody's posed any questions from so far from the Q&As.
So if they're panelists, they can mute themselves and ask directly.
Okay, so people and the panelists, you can unmute yourself and ask questions directly. Anyone? So can I ask a question?
Certainly.
Yeah,
Yes.
sure. So
Of course.
So this is okay from PDEs. These are just a lot from large numbers. So if you look at fluctuations, so we'll expect to get SPDs, and then it'll be also interesting to look at invariant measures for the SPDs, right? So will these techniques like the H-theorems, these will be applicable to study the SPDs?
Yeah, so thank you for your question. So actually with Haya Kaspi in 2013, we actually derived fluctuation, which is an SPDE. And in joint work with Agajani, two papers with Agajani, we actually showed the uniqueness of the invariant distribution over there. And we actually proved convergence to the invariant distribution as well. But what we didn't have over there is that we do not have a characterization of the invariant distribution. So here, because it's a fluid limit, you can use the heuristics to see what the invariant state should be. But in their case, we used actually the framework of unique ergodicity and the asymptotic coupling, the techniques of asymptotic coupling, to show that the SPD has a unique solution. So actually, those techniques could also be interesting in biological applications, looking at fluctuations. If you look at a particle approximation and then look at fluctuations, I think those kinds of SPDEs, we were able to show that there is a unique invariant distribution under some conditions, of course, on the G. This is already published work in the Annals of Applied Probability with Agajani from several years ago. But with Pooja Agarwal in her thesis, which is not yet published, we've also showed that that is true for the case of reneging. So we have studied the fluctuations in both these systems, both in the absence and in the presence of reneging, and we are able to show the existence of a unique invariant distribution. But whether you have convergence to it and whether you can characterize that invariant distribution, I think those are the interesting open problems.
Yeah, and also interchangeable limits, right? In that context, probably,
Yes.
I think it's,
Yeah.
yeah.
Which is sort of related to whether you can actually there, the interchange of limits follows from the uniqueness of the invariant distribution there, because you're starting with an invariant distribution. Here, you need to really show that if you start from any random initial distribution, even though it's a deterministic equation, you have uniqueness. That's the difficulty here, which you show by showing that you start at any deterministic initial condition, you converge to that. But in the case of already a stochastic system, if you show uniqueness of the invariant distribution, then you actually have the interchange.
I see. All right, thank you so much. So there, I see there's a question from audience. Binan Gu. So the question is this limiting procedure generalizable to an open or closed Jackson network of servers rather than parallel servers, or are networks still intractable?
Yeah. So there are several answers to that. So one is, yes, if you have a Jackson network of just single servers, that's very classical. It goes back to, lots of works by Riemann, Xavier, Diamarnik, and lots of people. But if you have a, sort of system of many server queues, then there's been some work, I think maybe even by Pang and Kang, and looking at sort of networks of many server queues, just looking at the scaling limits. So maybe the short answer would be that you can extend these scaling limits to more complicated networks. One of the key things is you can, in principle, I should say. But then the more complicated thing is, can you prove uniqueness? So you could probably write down quite easily what you expect to be the PDE limit, given what we already know here. But then one of the key questions is, can you actually show uniqueness of that PDE system? So if you have feed-forward networks, I don't believe it should be a problem at all. But if you have things with feedback, you will need some constraints on the feedback mechanism in order to get uniqueness of the limiting PDE. And then, of course, the analysis of the dynamics and the long time limits will be even more complicated, but it's definitely interesting. Yes.
Yes. Well, thank you. I think that answers the question. Let me see. There's another question. No, that just okay. Yangu just said, okay, reneging out of network sounds realistic as well. So that, thank you for the answer. Okay, so if no more questions, I think we, in terms of time, so we can close the session. And we'd like to thank Kavita again for the very nice talk to the seminar.